Welcome back to AP Calculus. This is our last section of Chapter 4. Should be receiving the chapter review practice test. And we've got one section left. One of the biggest challenges, it really shouldn't be a challenge if you decide, but otherwise one of the biggest challenges of this section is going to be you're going to have a lot of derivative formulas you're going to need to know. And we're going to introduce some more with those, as you can see. Hopefully I'll have it downloadable next to this video if you don't pick this up in class. But we got derivatives of inverse exponentials, and an inverse exponential, basically an inverse exponential is a logarithmic function. Exponential functions would be where we have a variable in the exponent. So this tells us that the derivative of a function, if we're taking the derivative of e to the u, we just get e to the u times derivative of u. That's the chain rule part. That's the baby derivative. So if, as an example, we're just finding the derivative of e to the x, that is e to the x times the derivative of x1. So e to the x is its own derivative, which is somewhat remarkable until you really have a really good grip and understanding on e. Whereas if we had e to this, now we have a baby function. So our outside derivative is the derivative of e to something. The derivative of e to something is just e to something. So this is e to the 4x cubed times the derivative of the baby function right here. Parentheses always help me see that. That's taking the place of u. Our function u has been substituted for 4x cubed here. So what do? We get e, leave u alone. That's the outside derivative of the inside function. Here's times the inside derivative. Or we want the mother function, which e to the stays e to the of the baby, u, treat the baby. So I have to treat the baby not in the exponent. It's always times. I get 12x squared. So we might want to write that as 12x squared. Oops, that's bad. 12x squared e to the 4x cubed. Or 12e to the 4x cubed. Or 12e to the 4x cubed times x squared. Okay. We just definitely want the 12 out in front. All right, so kind of an interesting one. The derivative of e to the x is e to the x. And that should be all we need to know that the derivative of e to the 4x cubed is e to the 4x cubed times the derivative of 4x cubed. Okay, then we have exponential functions here. This is where we have something that's not e, such as 5 to the x. It says the derivative of a to the u is just a to the u, but we have to compensate by multiplying by ln of a. And then times the inside derivative. So 5 to the x, we follow this. Well, the derivative of that is 5 to the x, but we compensate with ln 5, and then we multiply that by our inside derivative, but in this case our inside derivative is just derivative of x1. So our final solution is just this, 5 to the x ln 5. So the derivative of this would be 4 to the 3x to the 4th minus 2x ln of a, that's 4, is in that position, times 12x to the 3rd, our baby function's derivative, minus 2. Now, it's important to note that this ln 4 stands by itself. This 12x to the 3rd minus 2 is not a part of the argument on ln. So you may, just to keep from having confusion there, switch these two factors. You may want to write that as 3 to the x to the 4th minus 2x times 12x cubed minus 2 times, put the ln 4 at the end, or if you want to wrap parentheses around that, just to make certain that we're not letting this invade the argument on ln. Okay, so a little bit going on there. You're going to have some things to memorize. Derivative of ln u is just 1 on u. Derivative of ln u is just 1 on u times the inside derivative. That's our chain rule in action again right there. So derivative of ln x is just 1 on x, and I've given you that derivative prior to this, times the derivative of x, but the derivative of x is 1. So derivative of 6 times ln sine x is 6 times, or 6 on, sine of x times the derivative of sine of x, treat the baby, cosine of x, and if you're a little bit trigonometrically clever there, we quickly see that 6 cosine on sine, but cosine on sine is cotangent. That'll rear its head quite a bit on these types of problems. So 6 cotangent x. Kind of neat. Well, we would expect derivative of log of some other base other than e to be similar, and it is. It's still 1 on the function, just like this, 1 on u. It's still 1 on u, but we compensate for this not being e by multiplying by ln a in the denominator. So log base 5 of just plain old x, this isn't a chain because it's just plain old x, is 1 on, u is our argument, 5 times ln, excuse me, u is our argument, x, sorry, times ln, we want ln of our base, ln 5, times derivative of x1. Ooh, let's see if I've got room for this guy over here. Equals, well, we're going to have a -2 times, I know this guy's going to go in the denominator, 6x squared minus 3x times ln a, this was base 4, so that's not ln base 4, ln 4, and then times the inside derivative, or the inside derivative is right here, baby derivative, times, I'm going to put that in the numerator, 12x minus 3. Doesn't go down in the denominator, it's times outside of the fraction. So 12x minus 3 on 1, can put it up here, distribute, see if we can simplify things. Looks like maybe we might be able to divide by a 3, cancel a 3, little simplification going on there. Okay, nothing new here. This is just our power rule, no big deal. All right, let's take a look at some examples. Find dy dx. Remember, you can use n-derive to support your computations. We may talk about that in class. Okay, y equals 2e to the x. So we want dy dx. Anytime there's a constant times a function, the constant just survives, and now we just need the derivative times the derivative of e to the x. But e to the x is special. The derivative of e to the x is e to the x. Then we would go times the inside derivative, but x's derivative is 1. So that's it. 2e to the x is its own derivative. B, now our inside derivative, our baby function, is going to have an effect. So dy dx, e to the just wants to be e to the, but times the inside derivative of the baby function, -1, so we get negative e to the negative x. Or if you like, 1 on, -1 on e to the x. If you're trying to match back of the book answers, perhaps it would look like that. Okay, I might think of this as e to the 2/3 x. Pretty similar to that, but clearly that's e to the 2/3 x. So our rule for that would be dy, not much room here on this handout, dy dx, e to the, and you might want to leave some room out in front of this. Had I left room out in front, I could have put the -1 in front here. E to the wants to stay e to the. But we have to multiply that by the baby derivative. So that is times 2/3. You could put 2/3 out in front of this or make this 2 on 3. 2/3 times e to the 2/3 x. Okay, we got a little product rule here, x times e squared, or do we? We could kind of a little bit tricky here, but if we treat this like a product rule, what it would be? First times derivative of second. Well, what is the derivative of the second? And you may say, well, we got a rule for e. So the derivative of e to the second is e to the second times the derivative of 2, but the derivative of 2 is 0. But isn't e to the second's derivative just by itself? E is a constant. 2.71, something like that, squared, it's still a constant. This is just a constant times x. So dy dx is just e to the second. It's no different than this said x times 7. What's the derivative of x times 7? 7. Minus, what's the derivative of e to the x? E to the x. Can I do anything with that? Well, let me ask you this. Could I do anything if I had x to the 5th minus x to the 2nd? Can I smash those together in any way? No, they're different bases. If they were multiplied or divided, we could do something with that. So kind of sneaky. E to the second, just like pi to the second, just a constant, treated as such. Constant survive differentiation. So e to the second survives, but the derivative of x is 1. Okay, we may want to think of this one as y equals e to the x to the 1/2. We're going to have to take that baby derivative. So dy dx, don't have a lot of room here. I'm going to have to work horizontally, not my favorite thing to do. The derivative of e to the wants to be e to the x to the 1/2. But I have to multiply that by the baby, treat the baby, the derivative of x to the 1/2. So that is 1/2 times x to the negative 1/2. Or, let's see, what stays in the numerator? 1 does. E to the x to the 1/2 stays in the denominator. This 2 goes to the, or excuse me, stays in the numerator. This 2 goes to the denominator. This x to the 1/2 goes to the denominator. And take a look at that. I just get e on 2. Interesting. Maybe we could make a supposition at that point. Okay. Let's move on. Here we have x to the e. Well, do we treat that one special? No, we're used to dealing with things like x to the 5th, or x to the 9th, or x to the 20th, or x to the 1/2. dy dx, e is just a number. So this is going to be e x to the e minus 1. Now, how we might simplify that, we got some ways we could, because we could say this is like ex to the e times x to the negative 1st, and put that x in the denominator, so it could be actually ex to the e on x, but I think I like this just as much as that. So don't let the fact that we've got square roots or e's or anything that's a constant up here, we're just going to treat it as though it were 6. Then make it 6x to the 5th. Or negative 2 and make it negative 2x to the negative 3rd. Or this guy, dy dx equals negative root 2x to the, reduce this by 1, negative root 2 minus 1 power. Okay? But now, I don't make this x times 8 to the x minus 1. I will give 0 credit for that. This is an exponential function, and we're going to recognize that as an exponential function. So our rules, when we have an exponential, here we go. We've got some value of a raised to a function is a to the function times ln of a. So using that, the derivative of this is, it wants to still be 8 to the x, but I compensate for that with ln of 8. And then I take the derivative of the inside function, but that's just 1. So 8 to the x, ln 8. Likewise, dy dx it wants to just be 3 to the cosecant x. Just treats it like it was e, but it's not e. So to compensate for that, we go ln 3, and then we multiply by, outside of the ln, we multiply by cosecant's derivative. Cosecant's derivative, of course, we all know that now, is negative cosecant x cotangent x. So let's see what all we get here. I don't know if there's too much to simplify other than maybe we should put that negative out in front here. So maybe negative 3 cosecant, maybe the opposite of 3 to the cosecant x times cosecant x cotangent x times ln 3. Or, you know, we can play around with that all we want, match the book. Maybe it's negative ln 3 times 3 to the cosecant x, etc. Cosecant x, cotangent x. So we can play around with those factors, but I don't think anything's going to simplify real well for us there. X to the ln x. All right, no big deal. dy dx. X to the wants to be ln of x times x to the ln of x minus 1, but we have to treat the baby function, derivative of ln of x is 1 on x. All right, this one we're going to simplify. Let's see, I don't have a lot of room here. ln of x times x to the ln of x minus 1 all on x. If I had x to the 5th on x to the 2nd, we know that we would just turn that into x to the 5 minus 2. Therefore, we get ln of x times x to the, I took 5 minus 2, I'm going to take this minus 1, and I get ln x minus 2. Now, please note, that is not ln of x minus 2. It's ln of x minus 2. Okay? All right, so just a new look at, kind of just a little twist on things that we should be pretty comfortable with. Okay, so now we got some derivative of ln's, and derivative of ln's, where are we here? Derivative of ln just wants to make it 1 on the thing, but then of course might have to treat the baby. So ln of 7, ln of x is 1 on x. ln of 2x is 1 on 2x, but times 2. So let's take a look here. dy dx, ln x squared, it wants to be 1 on x squared, but we have to treat the baby function next times 2x. A lot of times, once we do some of these, we just won't even put the 1 in there, because whatever we treat x with could go up here. So that's times 2x, or dy dx equals x's cancel, I get 2 on x. Okay. So dy dx equals, how about we do this? This wants to be 1 on x. Then I need times, I'll put the 1 here, times 1 on x's derivative. I'm going to make it x to the negative 1st's derivative. Not a whole lot of room here again. dy dx. I may rerun these prior to passing these out to you and give you a little bit more space. So what do we get? 1 on x, flip and multiply, becomes 1 times x on 1. This is just x, times, I still have to take this guy's derivative, negative 1 x to the negative 2nd. That equals negative 1x on x squared, or I'm going to put it back up here, sorry. I get dy dx, negative, the x's, one of the x's cancels, and I get negative 1 on x. Okay. All right. dy dx, the derivative of the ln just wants to be 1 on the argument, but we have to treat the argument. Well, what is the argument? X plus 2. What's the derivative of x plus 2? 1. So it is just this guy. Y equals dy dx equals ln of something. The derivative wants to be 1 on something. But times, treat the baby, derivative of 2, 0. Derivative of cosine is negative sign. The opposite of negative sign is sine. So probably back of book answer would be sine of x on 2 minus cosine of x. Can I easily split this into two fractions? Sine on 2 minus sine on cosine? No. Can't split up the denominator like that. All right. Here we have a chain rule, ln inside of ln. It's not going to freak us out. We know the rule. dy dx wants to be, I want the outside derivative, 1 on the inside function, so it's 1 on ln of x, times the inside's derivative. Well, that is 1 on ln x times the derivative of ln of x is just 1 on x, so I get 1 on x ln x. I do not get 1 on ln x squared. This is not in the ln. It's not governed by it. It's a little bit dangerous to make it x times x out here. Probably want to put the parentheses, but best would be left to leave the x out in front. Okay, just some new tricks. The challenge isn't the calculus involved. The challenge in these really hasn't hardly at all been the trigonometry or the algebra. It's just, will we know these new formulas when it comes time when we have to know them, and we don't get to just come back and look those up. All right, let's continue. Find derivative. Derivative log with a base other than e. Here we go. Log with some base. It wants to be just like ln, 1 on u. But it's not ln, so we have to compensate with an ln of the base. Times the inside derivative, chain rule. So, log base 4 of x squared dy dx wants to be 1 on x squared. But we compensate, because it's not e, base e, with ln 4. ln of the base. Times the inside derivative, 2x. So we get dy, finally we got some proper room here. X reduces, 2 does not reduce. X reduces this to a single x, ln 4. Do not make that ln 4x. Not unless if you're going to do it, then the best way to do it, if I got ln 4x, boy, that could be confusing. You better do something like that. Make it really clear. Better would be this. Okay, good time to try some of these. You can pause at any time, of course. I'm not controlling your computer. dy dx, derivative of logarithms want to be 1 on 3x plus 1. Note the parentheses. But we compensate for that because it's not e with ln 2. And then we take times the inside derivative, that is 3. So we get dy dx is 3 on 3x plus 1 times ln 2. No parentheses, big time missed credit there. Nothing to it by this time. dy dx, log of not e, wants to be 1 on the argument, 1 on x. We compensate for that, since it's not ln here, with ln 2. Then we still have to take the inside derivative. I need the derivative of x to the negative first. So let's see. This 1 on x, if I multiply by x on x, can come to the top. Times this derivative, this would be negative 1x to the negative second, all on ln 2. I brought that 1 on x to the top. Or I get, let's see, a negative times a positive is going to be a negative x. These x's to the bottom, x squared to the bottom, ln 2, not ln squared, ln 2, or dy dx equals, x's cancel, but the negative survives, x ln 2. Okay, so at first look, we might think product rule, but ln 2 is a, I heard you said it, constant. That's a constant. This is no different than if this said 3 log base 2 of x. Constants survive the derivative process. I assume there's supposed to be a y equals here. So dy dx equals constants survive. I'm going to put it in the numerator. ln 2 times would normally be a 1 here. I'll put the 1. That's fine. It wants to be 1 on log base 2 of x, but we compensate with that with ln 2. Not this ln 2, but the rule is, because it's not base e, we got to compensate with ln 2 here, times the inside derivative 1. ln 2's cancel, and we get 1 on log base 2 of x. dy dx. Oh, this isn't so bad. All right, in calculus land, there's something special about e. There's nothing special about log base 10. We treat it just like it's log base 5. We don't have a special rule for it. So, outside derivative, the derivative of a log wants to be 1 on the argument, e to the x. Holy cow, I got to go back and redo d, that's for sure. Got to go back and redo d. That was just silly of me, my fault. I hope you saw that mistake on it. But let's wrap up this one. I just caught it. Wants to be 1 on e to the x. Because this is not log base e, ln, we make correction with that with ln 10, and then times the derivative of the inside function, which is e to the x. Well, the derivative of e to the x is e to the x. We've learned that. So times e to the x. E to the x's cancel, and I get y equals 1 on ln 10. E to the x, no, e to the x's cancel, yep. 1 on 10. Okay, let's go back to d. That was just a disaster here. I get ln 2 dy, I'd remake this if I wasn't almost done with it. ln 2, that's a constant, times the derivative of log base anything just wants to be 1 on that thing. Not 1 on the whole log right there. Apologies. Times ln 2, we compensate with ln 2 here, times the inside derivative 1. So we get ln 2, that's ln 2, the constant survives, and ln 2 cancels ln 2, dy dx just equals 2. That does not seem like that. Oh, no. Equals, what do we get here? ln 2, it's not 2 at all. Sorry. Again, still messing up this one up. 1 on x. That makes sense. The other made no sense whatsoever. Okay, sorry. Messed up on d a couple times. Let's go ahead and move on here. Use technique of logarithmic differentiation to find. I'm running out of time here, so this is going to be another video that we'll take at another time. But this logarithmic differentiation, I'll attach that as a second portion of this. This is a really